Now, we are going to understand what is a reference configuration. And what is a current configuration. I will not be picky in defining these things precisely, but I will communicate it in a sense that you can understand. Say at some instant in time t equal to t naught, which can be at 0 time, I assign a coordinate system, I choose a coordinate system x, y and z, and then fix the geometry of the body in this coordinate system. Let us say I took the body as this, okay. I took a body as this in that coordinate system. I have applied no load, but I measured what is the length here. This length may be 2 meters, this length may be 0.5 meters and this length may be 1 meter. Okay. So, I found all the dimensions of the body. So, I mapped on each point in the body to some point in this xyz space. Okay. Now, after I apply some load, the body would have deformed and it would have moved to some other configuration, which is say I applied load in this direction and in this direction. Okay. So, what would happen? The body would have deformed by elongating here and elongating in these two directions, but shortening along this direction. But shortening along the other direction, right. Now, this red one is called as the current configuration. Okay. The red one is called as the current configuration, meaning the configuration in which the body attains at some time t. This at time t, okay. At time t the body would have been in the current configuration. Okay. Now, to specify things, let us again draw the coordinate system x, y and z. I will draw potatoes for body this time. There is one potato here, and in the current configuration I will have one more potato, which is the current configuration of the body. This is the current configuration and this is the reference. Okay. Now, I pick a point in the body, and I denote the position vector of that point in the reference configuration by capital X. Okay, that is the vector. The position vector of the point in the reference configuration is denoted by capital X. Similarly, the position vector of the point of the same point, the current configuration will be denoted by another vector, which is small x. Okay. To elaborate, capital X is the position vector of a particle in the reference configuration, and small x is position vector of the same particle in the current configuration. Okay. Now, there are two things here, one is displacement of the body and the part taken by the body to reach the current configuration. Okay. First, let us understand what displacement of the body is. Displacement of the body is, displacement of the particle P is this straight line that joins these two, this is the displacement of the body. Okay. Displacement of the body is the straight line joining the reference position to the current position. Okay. Displacement is U is the straight line joining the position of the particle in the reference and current configuration. Okay. What is U in terms of capital X and small x? U would be from parallelogram law of addition x minus capital X, because x plus U will be small x. So, U is small x minus capital X, that is a displacement. In contrast to this, there will be a part taken by the body, that is this point need not move from here to here by this straight line which connects the two particles, but it can take a path something like this. This might be the path traversed by the body, this pink one is path travelled by the body, by the point, by the particle. This is not a displacement of the particle. At different instances in time, this displacement will have different values. Okay. So, how will you specify how this displacement, what variable this displacement depends upon, we will see next. Okay. How do you prescribe this displacement field is what we are going to see next. Clearly, this displacement is not going to be a constant, there is going to be different displacement for different particles in the body. Okay. So, this can be written as U can be written as a function of capital X comma t or as some function of small x comma t. How we will see now. Okay. Now, we understood that displacement is a straight line that connects the reference position of the particle with its current position of the particle. Okay. Now, we want to understand that this small x, how we can write small x or capital X as a function of time. Okay. So, I can write small x as some function of capital X comma t. What this means is, I am telling, if you tell me what was the position of the particle in the reference configuration, I will tell you what is the position of the particle at any time t from there on. Okay. So, this is called as the motion field. Okay. If I drop the dependence on time, if I write psi as a function of capital X alone, this is called as deformation field. Okay. Now, I use this equation to write my displacement as U is small x minus capital X. So, this becomes psi a function of capital X comma t minus capital X. So, this becomes U hat capital X comma t, this is some function of capital X comma t. Okay. So, now what does this mean? This means this will tell you how much a particle whose position it occupied was capital X moves or displaces with time. What is the displacement of this tells us what is the displacement of a particle that occupied the point capital X in the reference configuration. Okay. Now, this deformation field or motion field has to be 1-to-1 properties of motion field. You will see one of them today, the rest you will see later. It has to be 1-to-1, meaning each particle in the reference configuration will be mapped on to a unique particle in the reference in the current configuration. That is, the domain for each point element in the domain, there is a unique point in the range. Okay. So, the property of the motion field is it has to be 1-to-1. Why should it be 1-to-1 is because you are not going to allow separation of particles, separation of surfaces. That is, you are not going to allow one particle to become two particles, or you are not going to allow two particles to fuse into a particle, okay, into one particle, okay, which means a particle is occupying a point in space will occupy only one point in the current configuration also. Okay. So, that is what we mean by the motion field being 1-to-1. Okay. Now, since this is 1-to-1, I can invert the function, right. 1-to-1 function means I can invert this and write capital X as some inverse function of small x comma t, right, because since psi is a 1-to-1 function. Okay. It is a 1-to-1 function, I can invert this function. Now, I substitute this for capital X in here, I substitute this for capital X in there, then what do I get? I get u to be small x minus psi inverse of small x comma t, which is u, let me say this is another function of small x comma t. What this tells us is, this tells us what is the displacement of a particle that is currently occupying the point small x in space. Okay. Now, by the way, this way of writing the displacement is called as, this representation is called as spatial or Eulerian description. Okay. And this way of writing the displacement is called as the material or Lagrangian description. Let us understand what this means. In a material description, what you are doing is you are following a particle in the body and you are following it, how it is getting displaced, what is the displacement at different instances in time. On the other hand, if you are having a spatial description, you are focusing on a point in space. Say I am focusing on the tip of this pen, there is this chalk piece that moves on top of it. So, it moves. So, at different instances in time, different points of this chalk piece cross the observation point. So, they will have different displacements. So, this is what a spatial or the Eulerian description means. Okay. That is, you focus on a point and you look at what is the displacement of the particle that is currently occupying that point is. On the other hand, in a material description, you focus on all the particles that are contained in this chalk piece, and then you follow the chalk piece as it gets displaced. Okay. So, that is the difference. Now, typically in solid mechanics, you use a material description. This is followed in solid mechanics. When the body is a solid, you use material description, and you use in fluid mechanics, you use a spatial description. Okay. So, basically there are two ways in which you can write a displacement function as. The value of the displacement remains the same, but how you quantify the function, what you use to quantify the function differs. In one case you use the position vector of the particle occupied in the reference configuration as the independent variable, then it is called as a material description or Lagrangian description. On the other hand, if you focus on a point in space and ask the question what is the displacement of different particles occupying that point, that is called as the spatial or Eulerian description. Okay. And different branches of mechanics use different descriptions. We, being interested in solid mechanics, will use only the material description from here on. Okay. That is, you will write the displacement as a function of the position vector of the particles in the reference configuration as a function of time. Okay. So, what have we seen till now? We have seen what a body is, okay, and we saw what the displacement of, what is the displacement vector and how to represent the displacement vector. Okay. The final thing I want to motivate is why are we using 3 dimensions. Okay. We are using 3 dimensions because we have the concept of top and bottom, right and left, front and back. So, you have this 3 relationship which you want to quantify, hence you are using a 3 dimensional description for the body. But in many occasions you will find that such a description is not necessary. You can restrict yourself to either 1 dimensional or 2 dimensional descriptions of the body. That is an idealization that you make, okay, which serves a useful purpose. It is something like this: you consider the earth, you know, when you are living on the earth it is not a point mass, but still when you are interested in the planetary motion you consider the earth to be a point mass. The point mass seems to suffice to understand the planetary motion, but it does not seem to suffice to understand the occurrence of eclipse, right. So, in that case what you do, you consider the earth as a rigid sphere. Okay. So, such an approximation serves a good purpose to explain the eclipse that occurs, but it does not serve as a useful model to understand the behavior of foundation of a column on the surface of the earth, right. What you assume there? You assume that the earth to be a half space, infinite half space, but that infinite half space is clearly an approximation. You are living here, you know earth as a curvature and all those things, but still you go ahead with that assumption. And now if you are interested in studying the earthquake phenomena, what you do is you assume the earth to be a deformable sphere. Okay. You know earth is not a perfect sphere, but still you go ahead and make that assumption so that you get useful information regarding the different ways that travel on the surface of the earth and so on. Okay. In this perspective, it is not important what a body is in reality. The question you are asking is what is an useful approximation for the body that will serve a useful purpose for its analysis. Okay. In that sense, a body need not always be 3 dimension. For example, if you are interested in studying rigid body motions, you will consider it still as a point mass, because any distance from that point mass, any point in the body from a point in the body will be the same in irrespective of what force you are applying. Okay. So, there a point mass assumption suffices. Okay. Similarly, here you will assume that the body is 1 dimension or 2 dimension, 3 dimension, depending upon what action it is exhibiting, okay. And the continuum or discrete description is also in the same sense, it depends upon what you are interested in capturing at the end of the day, okay. So, going back to the concepts in mechanics,